This lecture is on severe weather and mid-latitude cyclones. We're going to look at what's taking place within thunderstorms and why lightning and thunder occur. So by the end of this lecture, you should be able to understand the severe weather within the thunderstorm and lightning. You should be able to understand the atmospheric conditions that produce thunderstorms and lightning, identify the clouds associated with storms, describe the evolution, right, the stages in the breakdown of storms, understand the inner workings of storms, what's going on inside, realize that severe weather is most common in the afternoon and evenings based on thermal lag time, and understand that lightning causes thunder, and most lightning, over 90%, does not strike the ground. It takes place within clouds themselves. The first thing we need to pay attention to with thunderstorms is that we're talking about unstable air, that this air is going to rise much like that of a hot air balloon, that the temperature inside the air that's rising is warmer than the air around it. So it rises and ascends vertically, and it creates these very characteristic anvil-shaped clouds that we call cumulonimbus clouds. These can be accompanied by heavy rainfall, lightning, hail, and strong winds. That it's believed that there are at any time on Earth's surface that there's 2,000 in progress, that there's 100,000 per year just in the United States alone, and they're most frequent in Florida and eastern Gulf Coast region. So we can see thunderstorms, the highest density here, or highest concentration, takes place where we have this maritime tropical air. We just have the conditions for the unstable air to rise. We have warm, moist air rising, and we have the conditions of thunderstorms that take place as a result. So a thunderstorm takes place from warm, moist air that rises due to this instability. The instability is what's driving the rising process, the buoyancy of the hot air itself. And this can take place where we have a high surface temperature, and it's most common in the afternoon and early evening. That's simply based on the thermal lag time. The stages in development of a thunderstorm take place. So there's first the juvenile stage. It's building. It's gaining its properties or characteristics. This is called the cumulus stage. We've got warm air rising. It reaches its dew point, forms a cloud. It continues rising above this. Once it reaches its mature stage, we still have air rising. It's still growing vertically. So we have your cumulonimbus cloud, but now we have air that's falling as well. Air that's rising can also cool. So we have these two features. We have air rising and air falling, and this can be associated with heavy rain, which is very common with the thunderstorm. And the final stage is the dissipating stage. This is where the air ceases to rise and it just begins collapsing or falling out from under itself. So when I look at these, the cumulus stage requires continuous supply of warm air and moisture. Each surge causes the air to rise even higher, and this is where we begin getting our updrafts and our downdrafts. The mature stage, eventually precipitation forms, and this is the active stage. We can find gusty winds, lightning and hail, and heavy precipitation. The dissipating stage means it's cool. The cooling effect of precipitation marks the end of the thunderstorm activity, that it literally begins collapsing under its own weight, and this can be associated with light rain. So how does lightning occur? Well, we talk about this air that's rising and falling here. That lightning is an electric current that occurs as electrostatic charges build in clouds. The ground is hot or warm and it heats the air above it. The air then rises and the vapor cools, right, adiabatically, and forms a cloud. As the cloud builds in its size, it grows upward. In the tops of the clouds, the air is below freezing point and the water droplets turn to ice. As the ice pellets collide with other ice, the charges separate and builds within the cloud. Charges build up, positive at the top and negative at the bottom. And so it's entirely full of this electric charge. So when the negatively charged base, when it grows large enough, a giant spark, what we call lightning, occurs between the two charges. Much like that when you rub your feet over carpet, lightning is just a giant static electrical spark. So here I can talk you through the stages of what takes place that leads to the lightning itself, but make sure you realize that the step leader is where you get the positive and negative charges that simply reach out to each other and connect, creating the electric discharge. And that lightning superheats the surrounding air and causes the expansion-contraction of the air molecule, and this is what generates thunder. Therefore, thunder is the result of lightning. In a fraction of a second, lightning heats up the air around it to incredible temperatures, as hot as 54,000 degrees Fahrenheit. That's 5 times hotter than the surface of the sun. The heated air expands explosively, creating a shock wave as the surrounding air rapidly compresses. Then the air contracts rapidly as it cools. So this is an animation you can watch. This initial crack sound is followed by rumbles of the air column that continue to vibrate. So as a thunderstorm rolls by, I want you to go outside, presuming it's safe conditions, and I want you to feel the heat of the lightning bolt on your face as the lightning is off in the distance. It's so hot you can actually feel that slight heating up. You can also feel the shock wave of the moving column of air on your body. You can actually feel it. Sometimes it can even affect the way you breathe. And lastly, count from when you see the lightning to hear the thunder. That every 5-second difference equates to about 1 mile distance at which the lightning storm is away. Anytime it's within 5 seconds, it's always best to be indoors. Here's a picture of ground strokes on Lake Michigan, multiple ground strokes. Clearly I would not want to be a fish in this area. Here we're looking at what happens when and why we see a tree literally explode, and we'll talk about that here in a moment. But we're really talking about the separation of charge. So when lightning strikes a tree, the sap, which is a poor conductor of electricity, it heats up very quickly. It literally boils. It creates internal vapor pressure that causes the tree to expand and explode. The picture at the bottom are what we call Lichtenberg figures. Lightning flowers are the branching features on the body as a result of a lightning strike. The water vapor on the surface of the human body vaporizes and it leaves scars. So also accompanying thunderstorms is hail. Hailstones continue to grow on upward and downward flights in a series of concentric spheres or layers of ice. Each of these layers represents a round trip. They're carried above the freezing line in updrafts. So notice, if I call these arrows here the freezing line, as it falls, this air down here is going to be above freezing. So it's going to gain another layer. The next updraft is going to take it up to freeze. The next layer down is going to add more moisture, and you get these concentric circles. That the temperature above the elevation is quite cold, well below freezing. So layering continues until the hail is too large to be pushed upwards and it falls down to earth. So here are actual pieces of hail, and they actually have concentric circles within them. It simply just shows you that there's updrafts and downdrafts that are constantly moving this ice itself. And last but never least, I just want to make sure you realize that airflow is very, very important to building and growing, to building hail, to getting it larger. And as it falls beneath this freeze line, it gains another layer of moisture that eventually the next updraft takes it higher, supercools it or freezes it, and it gets another concentric layer.